Cheers. Okay, so I want to set a few expectations. I wasn't sort of expecting to stand at the front and give any sort of talk. So not very much is ready in that regard. It's really meant to be a workshop for kind of rough coding. I wanted to get some people, whoever brought their laptop, sort of up to speed, maybe get Substrate downloaded and built, and sort of take people through maybe deploying a new chain, maybe writing some modules. Sergei here is going to sort of give a demonstration of how to deploy a smart contract on our smart contract-based Substrate-based smart contract chain. So yeah, don't expect too much hand-holding on this. What else? Yeah, I figured actually I would put it to the audience what it is that you would prefer to see. And do remember that, you know, if you say, oh, we'd like to see a new Substrate module being done, or we'd like to see how you develop the UI, or how we'd see something else, it is going to be me sort of bashing away on a keyboard for 85% of the time. And if you don't have a keyboard to bash away with in concert, then it's going to be pretty boring. But feel free to ask me to demonstrate or sort of educate on what Substrate does and how it works, and I'll try and use my now freshly compiled Substrate codebase to help explain. Any requests? No requests. Yep, Adrian.
Could you walk through how you can access Substrate modules with JavaScript?
I certainly can. It would be my greatest pleasure to walk through. Anything beyond walking through JavaScript? Walking through Substrate models in JavaScript.
On the main stage again.
Yeah. Sure.
And maybe also of how do I interact with? I mean, is it very similar to Ethereum? Does it use RPC? Can I use the same tools? How much different is it?
Okay. Sure. Yeah. That's going to be a month or two before we demo that. But yeah, you can expect that in the new year. Yeah. It's good that Rob's not here, otherwise he might be cringing right now. Yeah.
Could you perhaps explain what a UTXO model deployment would look like in general, and how it differs from the account-based model?
Sure. Yeah. Okay. I guess there's a few things there to be working on. Okay, let's start with the last question, because that's the one I can remember the easiest. So if we head to the part of the code base, is this? Can you actually read that, or should I zoom in a bit? Okay. Zoom in. Better, or some more?
Yeah, maybe 2 more.
Yeah. Okay, because like the more I zoom, the less easier it is for me. It's gonna get boring.
You can also push Command B to hide this sidebar if you want, to make more space.
Ah, yeah. Okay. Horizontal space.
Yeah.
Okay, cool. Yeah, so a UTXO model, it's an interesting sort of one, and one that we have just about begun prototyping in Parity. We've got a team of like 2 or 3 people working on it. Basically, the Bitcoin-style UTXO model is kind of an interesting hybrid between the strict all full nodes must validate everything, and base their validation, the things that they validate sort of, they put a state root, a storage root if you like, state root into each block header, and that means that light clients, when they come along, they can actually, in principle, validate everything, all of the state transition logic of every block based purely upon the state root of the last block, right? So if you trust that the header of the last block is something or other, then you can check that state root, and you can be provided with a proof that all of the transactions on the current block were executed correctly, and therefore that the state root on the current block is correct. And Polkadot very much uses this model. It's the model that the parachains are based around. And it basically means that validators, by having just light client logic, can actually validate every parachain equally. Bitcoin's a little different. In principle, if you trust the previous block's header, you can still be provided with a proof that the current block is valid, but the proof is potentially all of the Bitcoin blockchain, and therefore not super concise. This is the case because Bitcoin doesn't keep a track of the current state at every block and place that in the header as a cryptographic hash. Rather, when you want to sort of make some transaction on Bitcoin and prove that it's a valid transaction, you use unspent transaction outputs, and those are outputs that it is expected that nodes will record in their database, but if you want the actual proof that those outputs are valid, you have to go all the way back to the block where they were the outputs from a spend in order to be sure that that they're legit. And obviously, you have to see the entire chain between now and then in order to be sure that they weren't spent already. So it's much harder to do a UTXO model in literally the same vein as Bitcoin, because this kind of light client sort of model doesn't quite extend to the conciseness that Ethereum's does. That said, if you instead store the unspent transaction outputs in a Merkleized structure in the same way that Ethereum stores its contract state, then you are able to basically get a hash of that structure at every block, and you can provide concise proofs that a particular transaction is valid because you can see you can demonstrate that those unspent transaction outputs appear in this Merkleized structure. And that's how we would implement a UTXO style chain within the parachain model, and probably how we would implement it in Substrate. And that's actually going forward how it will be built. In principle, though, as I said, we could introduce a raw database into Substrate and actually mimic Bitcoin's model, but it would preclude turning it into a parachain without adding some additional layers of indirection and likely enough trust, which we're not so keen on introducing. Programmatically speaking, you'd introduce UTXOs at, if we go into the code base, so I mentioned before, like, Substrate has 3 levels of kind of, you can dive into Substrate at 3 levels. So you can dive into it at the core, which is right there, core. And this is, if you use Substrate, you use Substrate core. And it's got all of the things that you would expect to see in a blockchain. If we look at the modules, or the crates as Rust calls them, then you can see things like the consensus and the finality and the key store and the networking and the RPCs and so forth. It would likely be implemented as a outside of the SRML, so the SRML is here, because the SRML is rather designed around an account and an index model, similar to Ethereum. In principle, you could nonetheless create some additional SRML modules that kind of introduce UTXOs. In principle, as modules are Turing complete, they've got entry point functions that can be have arbitrary bodies, and they've got they can do basically anything with storage that they want. So there's no reason that you couldn't implement it that way, but it'd probably be a bit more efficient and would make a bit more sense if you implemented it as its own runtime. And to do it as its own runtime, you would basically just use the underlying abstractions in core that we used in order to allow things like the execute block function to be implemented and for it to be called into by the rest of the client, and work with that directly. And you define your own block format and your own transaction format, and in general build the execute block function that's in Bitcoin from scratch. As I say, Parity is pushing forward with a UTXO chain, mostly, so partly to make sure that the model that we have is actually general. It's a good sort of sanity check, and partly because we actually want to introduce a payment-based system a payment system that's based around UTXOs, and potentially that has some sort of ZK snark functionality in as well. And we're doing that with by reusing as much of the PBTC block Parity Bitcoin code base as we can. Cool. I'm not going to start implementing one here. Am I? Could start implementing one here. Okay. Maybe later. Cool. What were the other three questions? Theorem compatibility. Yeah. So how does the RPC and JavaScript work? This is an interesting question. So Substrate's meant to be pretty generic, and if we go to the RPC module, it's split into four submodules: author, chain, state, and system. Author is to do with block authoring, and it contains, let's have a look what it contains. Submit, extrinsic, there's a couple formats you can submit them in, and a pub sub to let you watch what's happening with those extrinsics. So if you actually want to if you want to communicate with Substrate through the RPCs, then these are the RPCs you're going to use. And it's basically like, here's an extrinsic, it's already signed, it's already done and dusted, just submit it, broadcast it, whatever, and let me know how it goes. And from this, you'll get back various messages, I think. Oh, no, they're on the, let's have a look. Maybe I've got some messages. No, I don't. You'll get various messages to tell you that it's been validated, that it's been broadcast, that it's about to be broadcast, that it's been broadcast, and that it's been finalized. Or if it doesn't get finalized, if something else gets finalized in its place and that it's now been dumped, then you'll be again told that it's been dumped.
What do you mean with extrinsics?
Okay, so back to Substrate 101. Yes, right. To make Substrate be as general as possible, we didn't want to introduce data into the block header that may not be in every blockchain that Substrate, that need not be in every blockchain that Substrate is going to cater for. Rather, we want to make the header strictly the information that is required for Substrate. The rest of the information that might otherwise go into a header in normal blockchains, for example, the timestamp, instead is provided under a separate model that's outside of the header called the extrinsics. And extrinsics just mean that it's like data that is extrinsic to the blockchain. So it's not intrinsic to the chain. It's not like part of its state or anything like that. It's not a previous transaction or anything that it can draw upon directly, but rather it's just data from the external world. It's extrinsic to the chain. And so data from the external world is provided in this set of snippets of pieces, and each piece is called an extrinsic. And it's just short for a piece of data extrinsic to the chain.
So for example, the accounts itself, you would determine this to be extrinsic.
So
As you have UTXO or just account.
right. So specifically, the transactions that are coming in from the external world, they are indeed extrinsics. So most blockchains, possibly all, require their sort of transactions to be signed. Like they have a particular signature scheme, and if they're not signed or if the signature's wrong, then they'll never be considered. They won't even make it into the system. Substrate's a bit different. So Substrate says there are perfectly valid extrinsics that are not signed. They're extrinsics, the only thing special about them is that they're a bit of data and they come with some way of determining their length up front. So you can pass them around on the network without worrying how long they are. Other than that, they're just arbitrary bits of data. They may be signed, they may include a signature, they may include a multisig, they may not. It doesn't really matter. Some pieces of data, for example, the timestamp. So there's okay, I can think of very esoteric ways how you might possibly argue that a timestamp could be signed and that would make it valid. Like maybe if the guys who run the atomic clocks like maybe signed it with one of their keys. But still, someone could steal the keys and then the signature. It doesn't make it specifically valid. Nothing can make a timestamp specifically valid, right? It's a piece of data from the external world, and the only thing that means a timestamp is correct is if we all agree that it's correct. What time is it right now? Well, I can say, well, it's 38 minutes past 6 in the evening, but if your watch says that it's 37 minutes past 6, then there is no way how, without like finding a shared authority, there's no way how we can argue that one is more correct than another, and certainly signing it isn't going to help.
To understand, so basically this function is used to submit any transaction or a transaction-like things. An author here is a name for that it comes from an external source, like an agent or like a person.
Author is just an arbitrary name that we call, when we say author, we just mean block author. So this is a block authoring API. This is an RPC that you use when you want to interact with the bit of Substrate that is authoring blocks. And this is actually incorrectly named. It's very good that you brought it up. It shouldn't be called extrinsics, or at least it's a little overgeneral to call it extrinsics. The only extrinsics that you can submit using this API are specifically signed extrinsics, because it's coming from the RPC, and therefore you have no other way other than looking for a signature to know that it's anything that's really sensible. Unsigned extrinsics, which for what it's worth we call inherents, because we treat them as being inherently valid, are generated within Substrate. So extrinsics is information that come from the outside of Substrate, and inherents are extrinsics that come from within Substrate. And transactions really come from the outside, inherents come from within. They're both forms of extrinsics because they're both forms of data that can be introduced to the blockchain and that might make some sense to the runtime. Now, if you don't sign some data, then it's like, well, how does that possibly work? If data's not signed, then it could be anything, right? And the way that it works is the validators, so the guys that basically say that this block is valid, are the ones that get to be opinionated over whether this data is sensible or not. And that's actually how this works in other blockchains as well. So if you look to Ethereum, if the timestamp is actually just an opinion, right? A validator, when they validate an Ethereum block, have an opinion over whether this timestamp is sensible or not. And if it's not sensible, they ignore the block. They unilaterally decide to ignore the block. And in that sense, Substrate is equivalent in its treatment of inherents. If it's up to a validator when they're proposing the block to put in sensible inherents, and if they don't put in sensible inherents, if their inherents are incorrect, or incorrect in the opinion of the other validators, then their block will be considered useless and won't get any further attention. So it's up to them to put in sensible values for the inherent extrinsics that are required by the block. And this basically means that we can do all sorts of interesting stuff, aside from timestamps. I mean, timestamps are the first use. But we can do things like, for example, with parachain candidates for the Polkadot relay chain. That's another form of inherence. Why? Because which candidates you choose in order to be there for finalizing is necessarily an opinion, right? It's different validators might choose different parachain candidate blocks to be finalized for that particular relay chain block. There's no way of deterministically choosing the correct set of these guys. It's just whichever ones happen to come by you. But if you put forward blocks that the other validators on the relay chain think are invalid, perhaps because they don't have the associated data, because there's no data availability for them, or just perhaps because they're empty, perhaps because they just haven't seen them before. Whatever reason it is, if they don't think that your opinion is a good one over the selection of these blocks, then they're free to ignore you. In reality, they'd have to be quite malevolent before they do ignore valid blocks, because they get paid basically for passing these things. But by and large, it's up to the validators to self-police the content of the inherent transactions. The inherent extrinsics. For the transaction extrinsics, they are per se valid or invalid. Like, you can check whether a transaction is valid by virtue of, does it have a good signature, and whatever account has signed it, does it have enough funds at this point in order to pay for the cost for it to be placed on chain. And if those two answers are yes, then it's all good. And that's the difference between the two. So this is the RPC for how you can submit them. Unlike Ethereum, we don't provide any account management stuff in here. So what you can't do is try and get it to sign a transaction. All of the signing happens external to the node. So the node is minimal.
But you have a key store package.
We do. Very well noticed. The key store package is there specifically for block authors, so for the validator nodes, to store their block authoring keys. So basically, when you set up a node as a validator node, so I got away without doing this on the demo that I gave earlier by using the --dev option, which is shorthand for --chain equals dev --validator --key Alice. But I could have typed those in and it would have done the same thing. And so when you pass it the key, it will use that. It will basically put that key into the key store, and then if it notices a key in the key store is one of the validators and it's set to being a validator, it will actually start signing blocks and join in with the consensus. So that's the key store is really just there for for managing validators' keys for consensus.
So if I want to have any kind of so if I want to do an Ethereum-like chain, all of the RPC methods which you, for example, currently have in Ethereum, I would have to actually build them in. They're part of a separate module.
Yeah, I can see. Yeah, so there'd be some shims or middleware in order to manage some of these RPCs to make it compatible. Now I'll go because this is kind of an interesting exploration, I think. So there are a few other modules. Chain does pretty much what you'd expect it to do. It's about blocks and headers. It lets you get transactions. As I have been chatting to Emil over last few weeks and months. The point of a Substrate node isn't to provide a generic, a sort of very generalized database for all of your uses that you might have. I mean, Ethereum was kind of pushing in that direction. We provided all sorts of lookups that we didn't really have to. Substrate keeps it minimal. It's got a fairly, that's one of its maxims of design. And one of the ways that we keep it, so one of the ways that this sort of minimal RPC comes out is the fact that you can't look up specific transaction hashes. You can, I think, maybe get, so you can get a block, and the block will come with a bunch of extrinsics, and in those extrinsics will be the transactions. And that's basically, if you want to index, if you want to have get a transaction by its hash, you're going to have to go to a chain explorer or a third-party service provider or whatever to get that. Now you can verify that's the case just by getting the block and transaction index and then going back to your node and using this RPC to get that block and then look up that index in the extrinsics, and you'll find your transaction or not. But we're not going to do that indexing for you because it's too much work, basically. It's better done on a dedicated piece of software.
But you could build this in as a module to actually provide this extra.
Yeah, sure. Or a shim, sure. Yeah.
Are all of the author and other features always available in runtime?
Or are all of the author and other extrinsics? You mean the entire chain's worth?
No, just for the current executed. If the block's not created yet, you get the timestamp.
If the block's not created yet, then you can't look it up at all.
No, I mean, when it's being executed, you get the timestamp.
When the block's being executed? No. So either the block has made its way into the database, it's finalized and it's good, or you can't read it at all.
Are any of the intrinsics available?
During what, sorry? Execution of the block? Or well, when a block executes, I can show you that code, but basically there's an execute block function, and you get given a bunch of bytes, and it's up to you to execute those bytes. So at the lowest level, so at core level, yes. At SRML, it's a lot easier, but that's full of a lot of opinionation that isn't necessarily indicative of your chain that you're writing on Substrate. Yeah, you just get given a bunch of bytes, and that's your block, and it's up to you to interpret the block as you desire. Uh-huh. Okay, let me go through the RPCs, and I'll come back to you. So yeah, we can get header, block hash, and there's also a runtime version. That should actually be in state, but it was a very late addition. Thank you, Tomek. I'm looking at the wrong people. Never mind. Thank you, Tomek. We have system, which just gives you a bunch of information about the system name, the version, and the chain. That's basically just the current running node. For example, we also have the JavaScript implementation of much of Substrate, and they'll return different things from these RPCs. Finally, is the state. This is the most interesting thing. So again, if we think about what you can query of a blockchain state in other blockchains, usually it's like account balances, whether an output is spent or not, how much is sitting there, potentially some state of a contract. You might even be able to make a a call into a contract and have it execute. We're a bit lower level with Substrate, as might be imagined from the fact this is a library with a framework with which you build blockchains. But the rough things that you can get from the current state of the chain are storage. So we have, at the moment, this RPC reflects a single storage database. So basically, we have a Merkle tree that is of arbitrary size keys and value pairs, right? So the tree itself stores basically any key value, any set of key value pairs, and the root is stored as the state root, and that goes into every block. As you change the storage, as you change these keys and values, then you can that will obviously change the state, and you can make. It's very handy for building parachains because you can make very clear like client proofs that one particular block with one state, given these transactions that executed, or these extrinsics, I should say, that executed, left another particular block with another particular state. That's nothing, not really any different to how Ethereum works. The main difference is that of generalization. And with our roadmap that where we want to build multiple different cryptographic databases. So if we think of the Merkleized key value storage that we have here as one example of a cryptographic database, then we want to actually extend this to other cryptographic databases and also add a means of having many of them at the same time. So if you're familiar with how Ethereum works, there is every smart contract actually has its own sort of cryptographic database where it stores its key value pairs, its storage, if you like, and then there's one sort of big one that all of these other, by virtue of them having state roots, all of these other databases hang off. Substrate only has one, but it's one very general one. And in principle, though, that can now be expanded to have as many as is desired, and they can even be of different types. And they can be dynamically added and removed in the similar way to that you would dynamically add and remove them in Ethereum when smart contracts go in and out of existence. We also have metadata, which is a wonderful RPC that I will spend some time talking about when I address one of the other questions, which was how the JavaScript magically works. And finally, we have a pub sub for storage, so you can subscribe to particular storage items, and you can get notifications when those storage items change. So if you understand how storage works, and that's one of the other magical things about metadata, that's what it kind of provides, that's what it partly provides, then you can basically keep an eye on that storage and just be notified when that entry changes.
Basically, smart contracts are higher level than that. So a smart contract could use a certain amount of storage in the chain.
Yeah, so Sergei can go into how smart contracts. So this little symposium will be will be split. So I'll answer whatever sort of more general questions about Substrate, and then Sergei's going to do a little sort of walkthrough of deploying a smart contract and explain some of the technicals behind the smart contracts, and we can go into the events and smart contract storage there. This is specifically for Substrate chains as a whole, and this will be very likely look like the final RPC and API for parachains. So if smart contract, so we have a smart contract module, and that exists as a module within Substrate's SRML. So you can basically make a Substrate chain that can manage smart contracts, as well as do a bunch of other things like have governance and all the rest of it. So we kind of see smart contracts as a piece of functionality that you can add to your chain or not add to your chain as you see fit, depending on your use case. Some use cases don't require a generalized sort of smart contract environment. Some are very sort of specific fixed function chains, and if they're specific fixed function chains, then, like for example, a plasma chain. A plasma chain doesn't require a smart contract module. It doesn't need smart contracts in there, right? It's a fixed function chain that would that basically manages all of the other chains hanging off it and what to do if those chains want to do an early termination or settle on the upper layer. So I don't imagine all chains to have smart contract functionality. In fact, I suspect many chains, even perhaps a majority of chains, won't have smart contract functionality. They'll settle for having fixed function, fixed pipe, fixed block processing functionality. That's upgradable because we like upgradability. Cool. So that's basically the RPCs. Now the interesting thing is how these interact with the JavaScript environment. So we're developing, because we like to give people choice, we're developing multiple JavaScript APIs to interact with Substrate and Substrate modules. Now these APIs are primarily geared towards interacting with the Substrate runtime module library, the SRML. So they are fairly, they're high-ish level, right? There are lower level components, like for example, you can use these pub subs with promises, I believe, at the JavaScript level. But if you want to, but we make it easy for you to use, to build applications based around custom modules that you code in the SRML. So you got a taste of that, although it might have sort of flown past you a little bit in the demo, because that was kind of trying to get it all finished and more or less on time. But I don't know if you noticed, but when I wrote that that little sort of toy, I was able to interact with the toy in the browser as soon as the chain had been upgraded. I actually, in the console, got like an object that that let me do it that was specific to the code that I'd literally just written in Rust. Now that wasn't a trick. I didn't have anything up my sleeves. It was literally that cool. What happened was the runtime got upgraded. Although I didn't code any new JavaScript stuff, what the code that I wrote, and annoyingly I don't have. No. Let me see if I can find that code. Should be in Substrate node template, and if I remember correctly, I might even have Gav demo. Yeah, I do. Cool. Okay, so so if we go back to the Substrate node template, so this is the sort of demo node that I forked and started coding, and I had this demo module. And if you remember, I did something like this. I said I did post sender and then decoded this little address, and then also for the call, it's calls.demo.setPayment, and that just worked. Despite me not actually having changed anything in the JavaScript. I didn't even reload the page, I think. I certainly shouldn't have had to. What happened was, when I coded this module with play and set payment, and when I coded this storage with the two entries here, payment and pot, part of this macro generates some metadata about what these functions are and what these storage items are. And this includes the types. This metadata is compiled into a sort of blob and then amalgamated with all the other metadata from all the other modules by virtue of this macro here, construct runtime, that you might have remembered I put the demo line in. This then gets passed to through this macro, which implements the APIs, into something that can be called into from the client. So we have here one specific trait that we can implement called metadata. It's a metadata trait. If we implement it, it means that metadata RPC will work. And what it will do is it will check to make sure it's actually implemented, call into it, which means dispatching into the newly compiled runtime that's been compiled into WebAssembly, and interpreting this metadata. And all this function does is it grabs the metadata from the runtime, and that was built from this construct runtime, and that was built from all of the individual modules, which each are built from their declarations of what their storage are and what their module is in terms of their function entry points. And this gets passed into the JavaScript. And as part of the Substrate JavaScript libraries, we have a couple of libraries that you can choose to use. One is based on observables. One is based on the bonds framework that I did last year. And these libraries will interpret this metadata blob and turn it into real JavaScript utility objects that reflect and will dispatch to and utilize all of the module specific stuff. So if we go to the where did it put it? Lib, no, this lib, no, demo. Yeah. So if we go to demo, then it will actually it will basically make marshal all the arguments and dispatch it through the transaction dispatch system into here. And similarly, if we query what the pot is, it will work out where this runtime, given that it's this module, stores the pot in its storage, and then go into storage and check that using the storage RPCs. And if you part of bonds is the fact that it's reactive. So if you tie that into a reactive component, if you remember at the end of the demo, I very quickly did a little label that tracked the pot going up and down. What it's doing there is it's setting up a pub sub with the thing that it figured out all on its own with the storage location for pot, and tracked the value. It knew what the type was because it looked to see that this pot type is T-balance, and decoded it into a balance type, and then put that into a label, formatted it correctly, and put it on the screen. And it did all of that without me really having to do anything other than implement it right here in Rust. So the idea with this is to make it not just painless, but actually fun to code modules and the UIs for modules. What was one of the other? There was another question. I can't remember. Mempool. Yes, this is an interesting one. So we rewrote the mempool. Well, Tomek, I should say, rewrote the mempool recently. We call it the transaction pool. But same thing. We wanted something that was general but also easy to use, and it took a little bit of thought. But what we came up with was a pool that basically allows runtimes to specify dependency graphs, arbitrary dependency graphs of transactions easily. We wanted something that would work equally well between a UTXO model and a account and index model. So basically a transaction pool that was equally viable to be used for something like Bitcoin and Ethereum, with the idea being that if we made something general enough for both of them, it would probably be pretty general, sufficiently at least for doing interesting other chains in the future. So the way it basically works is the runtime gets queried, and I can show you where this comes in. The runtime gets queried through this validate transaction as part of a tag transaction queue trait. So this is a trait that you have to implement in order for this transaction queue to work. Transaction pool. It actually just references the executive here. So the executive is like a sort of overarching SRML module that looks after just executing a block in general. In particular, it runs through each of the extrinsics and dispatches them off into the module that is expecting to, that the extrinsic is sort of trying to call into. All extrinsics in the SRML framework have they may or may not have a sender, they may or may not have a signature, they may or may not have an index, they may or may not have an era. We actually facilitate extrinsics or transactions to limit the number of blocks that they're valid for inherently, right? So you can make an extrinsic, or transaction, I should say, that is valid for the 16 blocks between 1024 and 1040, right? And after a block 1040, it's just no longer valid. It can never possibly be make its way into a blockchain. This is needed for a bunch of other things, particularly for having dust collection, which I can go into after I've talked about this, if that's of interest. The way that the validate transaction thing works, the important thing I want to show you is the inputs and the outputs. So the inputs are the transaction, fair enough. The outputs are is this transaction validity object. Let's see if I can find where this is defined. This is basically a means of, can we see? Yeah, here we go. So we can see it's got like 3 potential states: invalid, valid, or unknown. Invalid and unknown are pretty obvious what they mean. Valid, so for a valid transaction, we have a bunch of, we have 4 sort of fields that we have to define. Priority, so what's this transaction's priority amongst peers for which everything else is the same, right? So assuming that everything else is all other things being equal, which one should we favor to put into a block? For an Ethereum style chain, this would basically be, what's the gas price? If the gas price is higher, then we just favor it more. We also have requires and provides. So requires is, and we have this vector of transaction tags. Transaction tags are just vec_vu8. So in Rust, vec_vu8 is basically just an arbitrary bunch of bytes, right? It's just a byte string, yeah? And these tags, they're therefore entirely up to the runtime what tags it uses. It can tag them by hashes, it could tag them by integers. It really doesn't matter. It could tag it by account IDs. It could, concatenate a bunch of these things, and that could be the tag. They're entirely arbitrary. All that this transaction validity function has to state is what tags does it require and what tags does it provide. Now we can imagine for an Ethereum style chain, it would require, the tags that it requires are all of the tags. Actually, let's start with the tags that it provides. Tags that it provides are one tag that's formed by the concatenation of the account ID, the sender ID, and the current index, the index of the transaction, right? The nonce, yeah? So you pop those two together, that's your tag, right? That's just an identifier for the thing that this transaction provides. What it allows us to do is to then state what other transactions require in those terms. So suppose you have my transaction is sent from me, my account Gav, and it's got an index of, I don't know, 10, right? So for that to work in the Ethereum model, there has to be 10 transactions must have gone before, sent by me, one with index 0, one with index 1, one with index 2, all the way up to 9, yeah? And that would make 10 to be the next valid transaction. So what it requires is all of those tags. Now, that's a bit unwieldy for when we get into the thousands of, or tens of thousands of transactions coming from a single account. So what we say is only requires the tags that have not yet made their way onto the chain, yeah? And if we get into the silly numbers like hundreds, then we just say either unknown or invalid, and we just say, look, this transaction is just way ahead of schedule, send it back sometime in the future. And that actually is more or less the way that the Ethereum, the Parity Ethereum transaction queue sort of worked, just not in these terms. Now, if you're on a UTXO chain, then it's actually quite a bit easier, because a UTXO model, like basically, you've got what the tags are. Their tags are just transaction output hashes. Yeah. So your tags are, it requires these unspent transactions or unspent transaction outputs. So those transactions that are providing those outputs are specifically the things that are required, and it provides its own hash, its transaction hash. So you can very quickly build very easily build a dependency graph from a UTXO chain that maps like fairly well onto this. And we also have longevity. So longevity is basically, it's valid now, but for how many blocks will it continue to be valid in the future? For Bitcoin and Ethereum, that's infinity, basically. Transactions don't become invalid just because time has passed. But for our Substrate chains, we have this notion, as I said before, of eras, and the ability to inherently make an extrinsic or a transaction inherently invalid merely after the passing of time, or specifically blocks. And that's what this sort of lets the transaction pool know about. So yeah, that's pretty much how transactions work in Substrate. This is more for the SRML. It is meant to be general. So in theory, it can be used perfectly easily from the core, from if you want to build like your own from scratch Substrate chain. In principle, this can be used fine, but you're also free to write your own. Like there's nothing you can plug in your own queue if you want to write your own queue if you have something that this model can't manage to embed. The nice thing about this, though, is that it goes to the runtime for all of its rules, which means if you want to update your transaction formats and you want to introduce all sorts of new and crazy interesting stuff, as long as you can put it in terms of priority requires, provides, and longevity, then you can implement whatever it is that you want, and when you upgrade the chain, all of the full nodes, all of the authoring nodes, will all automatically use your new transaction semantics. And their transaction queues will function accordingly. Yep. You can't modify. So can you modify a transaction that's in the queue? So what you can do is if a transaction has made its way into the queue because it said, hey, it's valid, and you want another transaction to be able to beat that one to it, if the two are mutually, you can make it mutually exclusive by simply giving it the same tag but higher priority. That will get the transaction queue to sort of boot it out. The transaction queue only feeds transactions into the block. If you just want a transaction to just become invalid before it's been finalized, or before it makes its way into a block, you can do that just as easily by having a sort of, if in the execute block function, if one of the transactions is this transaction, then invalid block, right? And what will happen is the unlucky guy who's using this transaction queue to make a block will find that adding this transaction makes their block invalid, and it's kind of bad form to do it that way. You should try and make it as much of part of the queue as possible. But if for whatever reason you can't do that, then yeah, you can make it invalid just by virtue of changing the runtime. I'll get Emil first.
So suppose a Substrate instance or the Polkadot relay chain at some point runs fast, and the transaction pool fills up. Is there an inherent mechanism to select some extrinsics over
Tomek can probably offer a little bit more insight into this. Basically, priority is the first thing that it will select on, and beyond that, so for the transactions that have not yet become valid, then basically it's just randomly discarding ones. Not that random is particularly great, but it also minimizes any potential issues regarding censorship. So if you've got like tons of nodes on the network and you're really trying to prevent some particular transaction from getting through, and you're doing that just by spamming transactions out onto the network, we minimize the worst case by choosing transactions at random to discard, because it's likely that eventually one node will mine that transaction that.
So how would you prevent congestion?
Ultimately, if lots and lots of people want to transact at the same time, then there will be congestion. So it's really just a case of randomly choosing transactions to come through. I mean, in principle, priority here that's precisely what priority is for. At times of congestion, the runtime can basically state which transactions should be favored above which others. But if priority isn't enough, for whatever reason, maybe everyone's got the same gas price, or I don't know, whatever, or you don't introduce any particularly compelling prioritization mechanism, then random is the best we can do. Cool. What was the thing after transaction pool? I've forgotten now. Was there something else to discuss?
Smart contracts.
Yep. Okay. Anything before smart contracts? Yeah.
You mentioned earlier somehow you want your types to be opaque in order to allow grid load.
Yeah. Okay. Yeah, I can go into that. So. So the runtime encodes a lot about what a blockchain does, how it works. It doesn't encode everything in the substrate model, because we don't want some things to be specified. What we could do is literally just put a Rust executable on the chain, and when that changes, you have to kind of download the new one and run. But we don't like that. There are, I think. I may well need to be corrected here, but I think there is a certain other project that's trying to do governance and upgradability, and that's more or less the model that it takes. So it sort of basically puts its executable on the chain, and it's up to the nodes to kind of download the new executable and run that. I don't like that model. I prefer to be a little bit more conservative about the specific component that can be upgraded. And when we accept that part of the logic doesn't sit on chain, for example, the peer-to-peer networking library, I don't think it's sensible to put that logic on the chain. And there's even questions about putting consensus logic on the chain. It could be that if consensus logic is on the chain, then you have this kind of monoculture almost, monocultural strategy for the consensus, and that may lead to attack vectors by virtue of knowing that all of the nodes use the same strategy. So if we're happy with not putting all of our logic onto the chain, then the question is, given that we need to have the same data structures ostensibly on the chain, like in the runtime that's upgradable, and off the chain in the sort of general node itself, how do we manage the fact that sometimes those structures will be, those data structures, like transactions, for example, could be changed over the course of a chain's life? How do we like manage the fact that these transactions have to then be sent? They have to be stored in a transaction queue, and they have to be sent over the network. There has to be some way of handling these things, right? So we need some sort of object, and that's where these opaque objects come in. We need to, a block needs to have some characteristics, and there has to be some object that we can call a block. But we don't need to go into the specific meaning of a block beyond the basic semantics of here's how to read a block number, here's how to read the parent hash. And these very basic types are what we call the opaque types. And they are the fundamental types of a blockchain that don't change from Genesis onwards.
That you couldn't upgrade with on-chain governance, for which you
That in principle,
everyone has to download some new code and manually.
they're basically fixed. Now, then you say, oh, well, hold on, if the extrinsic format is fixed and the block format is fixed, and then surely you can't upgrade. And it's like, well, actually, that's the reason that they are opaque is because most of the data that they contain is not stored in terms of specific fields, like the real meaning, but rather it's just a blob, a generic blob. And it's only the bits of the data that we actually need to know. For example, we need to know the length of the transaction, or the extrinsic. Because if we're going to send it around, we need to know how long it is. And so what we do is if we're going to concatenate it together into a block, then we need to know how long each particular piece of the concatenation is. So we say, right, the one bit of a transaction, of an extrinsic transactions format is going to be the length, the prefixed length. But everything beyond that, we're going to leave undefined as to its meaning. We're just going to tell you how to decode and encode it. You decode it by reading the length and then reading that many other bytes. I'm not going to tell you what those bytes mean, but that's how you decode it. And you encode it by seeing how long it is and then putting the length at the beginning and then following it up with the other things. By avoiding defining this stuff, we can then define it in the runtime, and then as runtimes upgrade, we're not left with incompatible data structures for handling these things in the client. Now, it's important that this isn't something that we do with every type. It's just the fundamental types that clients do tend to have to be able to handle, basically because we need to pass these types around the network or because we have to interpret them for the consensus algorithm. So block headers, one type, extrinsics, one other type, and I think hashes maybe, although hashes are opaque data anyway. I think it's basically just those two types. Although again, signatures are opaque data anyway. So you've got two types of signatures that float around in Substrate. You have you have signatures on the consensus side and signatures on the transaction side. So signatures on the transaction side, they don't need to be the same. The runtime entirely interprets those. I can well imagine Substrate chains that don't have any signing, any cryptographic signing on them at all. That they're just, the validators choose which things come along, and they, from maybe some, I don't know, trusted corporate centralized database, and they're just funneling this data in, and it's going into the chain and just being recorded, and maybe there's some state transitions that happen on the chain. But basically, there's no need for signatures. The consensus side, yes, there are signatures, but I guess the consensus algorithms define their own cryptography anyway. I mentioned what, sorry? Yeah, so I kind of spent a while describing that, but I mean, I guess I can probably, if I can launch a node, do I have one already?
Can I have this?
Oh yeah, sure. Okay, so I have a node running. Okay, so this is, I think, the demo node. I'm going to upgrade it. Okay, so right, this is wrong. Just rerun it. Yeah, okay. So is that too small? I guess that's way too small, right? how do I, okay, like that. Is that still too small? It's too big. Okay. All right. Okay, so this is template node v2, which I think means the demo is in. But I can check this by. So I mentioned there was the runtime object. Fun time. Okay, so the runtime has a bunch of. These are the various modules in the runtime, right? So balances, consensus, core, demo. That's the one I just coded earlier today. System, timestamp, upgrade key, and version. These, as I mentioned, come from the metadata. So I can show you the code. I mean, it's I don't know how interesting it is. If we go into the 007, if we go into the 007 library and then the 007 substrate and then the bonds, this is where they get created. Let me see if I can make this a bit bigger. Okay, can you read that? Just about. Yeah. I need the drum player here. Okay, so these are the sort of easy ones that just that are just sort of hard coded: height, header, head, hash, name, version, and chain. I mean, you saw the RPC end of these. We have this node service that just ensures there's a single WebSockets connection to the node, so it's like a singleton, and then we can issue a request. These are single shot requests. Some of these, like head, they're subscriptions, so they use the pub sub functionality. We have runtime version, so I can give you a quick. Runtime, I think it was in the core, and then runtime, version, yeah, there we are. And then console log. And that's what comes back. Very simple, got the APIs. This exactly represents the structure in Rust that is in runtime lib or source lib in Substrate node template. Yeah, so this represents exactly this structure. If I change this structure and upgrade the chain, then this will automagically update. If I run this thing again, it will give me the new values. Yeah, and it's the it's not the metadata that encodes that, I think, but that is fetched from the runtime in the same way that the metadata is fetched. So the metadata is built automatically per module in the runtime, amalgamated together by virtue of a couple of macros, and then passed along into the JavaScript. And in the JavaScript, we have so we actually have a serialization library, very, very lightweight, basically just memory representation serialization library. And we have the opposite in JavaScript. So we can serialize and deserialize in Rust, and we have the same thing in JavaScript, and we can kind of a bit like JSON or whatever, except binary, and sort of designed to be very fast and very minimal, lightweight. Yeah, that's.
Question on that. Does the node run Webpack? Are you
Yeah, you mean these modules?
Yeah.
Yeah, so these are indeed, there is a Webpack running somewhere here. Yeah, so we've got like NPM sitting around in the background, updating, checking for changes and packing it all together. Okay, so there's two things going on. So the first is these UI components. those you have to code independently. So they don't come from Rust. They're not automatically made. You actually, if you want to add a new module, you have to sort of get your typing fingers out and go into wherever it was that I went into. Here we go. Yeah. No. Where is it? Here. App. So this is the UI, and this isn't special at all. This is just standard React semantic UI with Webpack and npm packing things and looking out and watching it and packing it in the background. So there's nothing. I don't. So if I add a new module, then I have to press Control-R. Yeah. But what happens? I didn't press Control-R just now to get. If I do a blockchain upgrade, I don't have to press Control-R now because the metadata automatically gets updated in the background. So that doesn't come from the thing I was mentioning earlier with the hard-coded things. So the bonds, these bonds here, the version bond and the name chain, height, header, hash, these are all hard-coded. They don't change. They're fundamental RPCs that Substrate provides. But the other things, the things like, if I go to runtime, then like, I don't know, balances. If I want to get the balance of an account, what accounts do I have? Let's decode an account. Yeah, let's decode this account. So I want to get the balance of this guy. Oops. Then I can decode that into an account ID and give it to balance and then print the output. And it's going to tell me that this guy doesn't have any money, I think. Yeah, balance 0. And then if I gave this guy some money, so let's send some funds to him or her, whatever. It's a hex address. I'm not sure if they have gender. Do I have any? Alice has got some. I guess Alice is a girl. And I'm going to send, I don't know, if I send 1,000 units, that's going through, sent. And then if I go back to, where are we? Balances, then we go, now it's got 1,000, yep. So this stuff, when we go into the specific runtime modules, they're not built, they don't come in by virtue of this code. This code builds them programmatically from the metadata that is, has a pub-sub relationship with the node itself. So as the node's runtime gets upgraded, this finds out about the upgrade, grabs the metadata, rebuilds all of those objects and data structures, and lets us now interact with the new runtime in a ergonomic fashion. But if we want to add UI components, then we have to go in and do them ourselves and press Control-R.
What encoding does Polkadot? Like the relay, like specifically Polkadot?
The relay chain. What does it use?
Like, what encoding format is Parity coding?
So Polkadot uses Parity codec. Polkadot uses basically all of Substrate. Right? There's not much in Substrate. Smart contracts is the only thing it doesn't use. And yeah, other than that, it looks pretty similar to our basic Substrate node. So it's got all of the sort of functionality in, apart from a smart contract, but it does have an extra module that's specific to Polkadot called Parachains module. So I'm not like, it's been a little while since I looked at the Parachains module, but that's something that will become pretty important over the next POC. So POC 3 was dedicated mainly to our new consensus algorithm. That will be the final algorithm for Polkadot. Shaft. Or Grandpa, I don't know, I mean, I do know, obviously Shaft, but some people don't, not everyone agrees. Yeah, sure. So Shaft is a well, actually, is Al here? Ah, damn it. So Al invented Shaft. At the time it was called AFG, Al's Finality Gadget, but we're kind of renaming it. And basically it's a progressive, adaptive progressive finality consensus algorithm designed specifically for Polkadot's use case. And the idea is that it adapts to network situations and validator pluralities. If you have lots of validators, if you have few validators and a really good network, then Shaft will finalize as quickly as an instant finality algorithm like Tendermint or Rhododendron, which is our sort of take on PBFT for the blockchain. But even if you have slower network and lots of validators, it will finalize as fast as it can behind the scenes. And the way it does that is by having a transitive relationship over the blocks. So the way that PBFT-derived algorithms work in general is you have a candidate block. So every block number that you want to finalize, every block that you want to finalize, there is a candidate, right? It's not yet finalized, so it's just one of many. And then you put it to a bunch of vault authorities or validators, the participants in this consensus game. And they will each, if it's a PBFT-based thing, they'll do a pre-commit to basically say, this is the one that we think should win. And then if they see enough other pre-commits, they'll move on to a commit. And there are rules about whether you can change from given that you've pre-committed on one thing, whether you can change your what you're allowed to commit to, and if you've committed on one thing, whether you're allowed to switch that commitment. And these rules basically guarantee that, assuming no more than 2/3 plus 1 Byzantine nodes or Byzantine participants in the game, that you will always come to an agreement on what it is that on a particular candidate. Now, this is fine. It's a perfectly reasonable way to go, but the problem is that it's not optimal because blockchains have relationships. Blocks have relationships between each other. So blocks that are all of the same number, so they're all at the same level, they're just different candidates for the same potential slot, don't have much of a relationship beyond being mutually exclusive. But blocks that appear before, so parents or ancestor blocks, have a very, very strong relationship, right? Cryptographic relationship. We store their hash, which means there's an implication that if you voted for block, I don't know, 68 in the chain, then block the block 67 that 68 references by virtue of its parent hash, you've also voted for that, right? You've also voted for 66 and 65 and all the way back down to the Genesis block. Assuming that the network conditions are such that you are not going to be able to afford to finalize every block, then a vote for 68 should definitely imply a vote for 60. For 67 and so forth, but for that 67, yeah. So if there's two forks, if there's a fork and it's made its way 2 blocks deep, well, okay, maybe it hasn't made. Yeah, actually, it could have, in principle, have made its way 2 blocks deep just at the production stage. Then it's important that any vote for 68 must imply a vote for 67. So what you're not allowed to do under this transitive model is both commit to 68 on one fork and to the 67 on the other fork. And that's one of the things that now becomes illegal. But because that's illegal, what it means is that we can interpret a vote for 68 as a vote for all of the blocks that haven't yet been finalized on that fork. And suppose we're the most recently finalized block is terrible network conditions. The most recent finalized block is like, say, block, I don't know, 50. Yeah. So we're running 18 blocks in advance of the most recent sort of agreed on head of the chain. Then, if we've seen, let's suppose we have 10 validators, and they're basically just they're just voting for the blocks that they see. We can only get out one vote per block, and it's our vote. So actually, that's not. We've got 20 validators, and we can only get out one vote per block. What would happen is that under Shaft, these votes, we would always be running at the 20th most recent vote because, actually, no, because we only need 2/3, so it would be the 13th or 14th most recent vote, because we can accept all of the votes that were on blocks after, let's say, where were we, 50, so suppose we're trying to finalize, like, I don't know, 53, yeah? All of the votes on that fork after 53, so every validator is like doing one vote per block, so one of them's voted on 54, one of them's voted on 55, one of them's voted on 56, all the way up to 67 or 68, wherever we were, then it's likely that every new block, 2/3 plus one, will have voted on one more than the last block, in total, accounting for those transitive relationships. Because every new block that's being produced, that validator will be voting on that new block, which will imply they voted on all of the blocks up until that new block, which will imply you've got one more vote, assuming a constant cycling of validators, one more vote on that chain in general. And so, because that chain's been brought forward by a block, because everyone's voting on that chain, then the most recent block to be finalized will probably be a bit further along. As network conditions improve, validators can get more messages out, then that will catch up naturally because a greater number of votes will be recent, and therefore, again, transitive relationships being what they are, you'll be able to basically form a consensus that 2/3 plus one validators agree that, in fact, 62 is the most recent shared block that they can all finalize. It's a pain to spot when a validator has behaved badly, basically because the rules are transitive. The rules are transitive, and so you have to enter into this, in the worst case, enter into this game of querying, well, hold on, you as a validator voted for this block on this chain, but yet you voted for that block on that chain. Why? What were you seeing? What signatures did you see that made you switch chains? And they can either equivocate and say, don't know, because they switch chains invalidly, or they can provide you with the signatures, in which case you have to go to the next guy along and say, well, you signed for this chain, but and the game continues. Basically, it's quite an unwieldy game, and it's a bit of a pain. It's a bit tedious to play, but it's something that can happen on chain, and it's not the end of the world. Beyond that, it's got some very nice proofs about how live it stays in an asynchronous environment, and it's optimal over the. It uses the notion of block transitivity optimally in determining, under a PBFT style mechanism, which is the most recent block that it can be considered final. Yeah, that okay? Under optimal network conditions, assuming the validators are well connected with each other and that their plurality, because I mean it's PBFT, so you can't get around this n squared message passing stuff requirements. But assuming that they're well connected and there aren't too many of them, then, this is where empirical measurements come in, but certainly with our testnet so far, there's no reason to think that we can't handle finalizing most blocks. So not staying very far behind the block production head at all. So the block production is handled by a separate consensus mechanism that doesn't provide finality. At the moment, we're moving towards ORAND, which is a randomized shuffled version of Aura, which basically just stands for authority round, and you just go around a bunch of, do a round-robin style block production game. But it's our intention eventually to move to probably something similar to Ouroboros, which is it's basically like proof of authority mapped on proof of work mapped onto a proof of authority schema. So authorities get given lucky slots whereby they can mine a block, and it's a way of generating these lucky slots and administering them in such a way that you get given a bunch of guarantees about Byzantine tolerance. Yep. So network topology or peer-to-peer networking in general. We're using libp2p, which is pretty modular. In principle, there's nothing that would stop you from writing a new module that would provide the sort of networking if you want something like onion routing or like mixed nets, I don't see why that wouldn't be possible using the existing network module system. Worst case, it's probably like implementing it as a new API, but that's something we'd look into. No, I think it's what you can build on top of it. I mean, we'd certainly be interested to sort of explore if the APIs are sufficient in order to provide that, but I suspect they might be. Okay, more questions. How long are we? Was it 8 p.m.? Do we want to? Maybe you think you?
It will be a little bit harsh, but
yeah,
I think.
Okay, let's maybe move the questions towards the end and do some exciting stuff. Do you want to plug in the HDMI?
Yeah.
I'm glad that you're doing this because I need to go to the toilet.
Yeah.
Have
you heard the news?
Do we have working toilets yet? Yeah? Outside.
So.
Sergei.
This thing seems to. Oh, fuck. Oh, cool. So let's get started. This demo is like wasn't prepared at all because of reasons, and I had to improvise. So yeah. Let's get started. Because I basically don't have any UI, because of, as I mentioned, reasons, I have to do I have to craft in extrinsics by hand, basically. Yeah, but I have some little code snippets that actually can help me with that, so it's not that problematic. Is it okay? Yeah? Okay, so let's start with a fresh chain. For that, let's that maybe make some take some time. Yep, yep. It's basically the branch. Yeah. Say again?
What if we can use the substrate not template repo?
No, I would say no. Because, yeah, for some reason I chose to use the Substrate repo. Yeah, so let's clear the DB and then let's launch this new chain. Yeah, so it seems to be working. And yeah, so let me check. So to make an extrinsic, we need some to do some boilerplate code, and for that we need a Genesis hash to like it is required to create extrinsics that can be executed on this particular chain. So we need to first fetch the block hash of the Genesis, and for that I'm gonna use the RPC. Get block hash. So I will call block hash function with argument 0, which is for Genesis block, and so oh yeah, actually it's already there. Yeah, and after that I will regenerate all extrinsics. So yeah. So this extrinsic, this big blob of opaque data contains instructions to deploy a certain contract, and the most of this data actually represents WebAssembly smart contract. And yeah, let's actually submit that extrinsic. Oh, have this one, but it doesn't. Yeah. Oh yeah. It should have happened. Yep. So to verify that it actually executed well, let's see the Substrate UI. And oh, really? Yeah. Do you have an idea how to look up nonce of Alice?
Yeah. Is this a network I can connect to, or it's
Uh,
just dev?
yeah, it's dev.
Okay. Yeah. So we've got a JavaScript shell here.
Yep. I think it's yeah.
Oh, is this Firefox?
It's
That's
Safari.
Safari. Ooh.
Oh, sorry,
Ooh.
sorry, guys. I have Safari if you want.
Okay. So yeah, the runtime, and then balances is where the hold on, it's not system where the index is stored, and then account nonce, and then which account?
Alice.
Alice. We should get Alice's. So we need to introduce the seed for Alice, which is a pain to do if you don't. Do you have subkey?
Yep. Try to just execute it. Yeah.
In here?
Yep, sure. Subkey.
Okay. Subkey?
Yep, just subkey.
Just works? Yeah, cool.
I hope.
But is it the latest version of subkey?
It's from RH Aura, but I'm not sure
Yeah?
it's
Okay.
latest.
It might work then.
Just try.
Restore Alice. Yeah, it does work.
Oh, cool. Totally unexpected.
Okay.
How can I help you?
I want to get the Safari up. Okay.
Okay.
Right, so we put that seed in.
You put it here. Okay, yeah.
That's Alice, and then so Alice has this.
Yeah.
Now this is a short. Oh yeah, this is something that should go over actually because this is kind of cool. But I'll do it afterwards. So we can try that. Oops, and then dot then.
Everyone can
log.
see what's happened there, right? Okay.
Oh, it doesn't. What? Safari doesn't have console.log?
I wouldn't be surprised, actually.
Okay. Then.
Maybe it's not about then part. I mean, maybe something nonce account nonce. No, looks good.
Okay, let's n equals 0. And then n is going to equal x. Oh, okay.
Maybe we should open Firefox or something.
Let's just check one more thing. SS58 decode, and then Alice's ID, then console.log. Okay, so that's done something that wasn't a type error, but it's let's n equals 0, and then x n equals x. Okay, what is n now? It's 1. There you go.
Oh,
Alice's nonce is 1.
So that means that our transaction actually got in, and we deployed the test contract. So now I'm gonna show what kind of contract this is. Substrate contracts are there. Yeah. So so this contract is basic counter, which has actually two functions, two actions that we can actually execute on it. Let me do something. Yeah, so the first one is increment that takes U32 parameter, which specifies by the value by which we should increment this counter, and get function which basically returns the value. And when the contract is executed, we just read input data. It's basically the same as in Ethereum, and decode it into this action enumeration. And then, depending on what actual variant of this enum, we performing the action. And this, in case of increment, we just query the contract storage by certain k, which is 32 once, and then decode it, increment by the specified value, and then save it back into the storage, encoding it before that. And get is basically just we read the storage and return that value, and that's it. Yeah, so this contract is already on this chain, and yeah, so there is an extrinsic that with which we can call this specific contract, and it takes address of that contract, and address is calculated by the constructor code of this contract and the origin address which sent this the create extrinsic. And with so again. Yeah, actually it's used, and it's specified right here. So for the first transaction, it was 0 extrinsic, and for the second one, it's 1.
Why is address not taken?
Yeah, okay, I see what you mean. For determining contract address, nonce is not used. Only code of constructor, origin, and just like input data, and that's it. Yeah, basically yes, but you can alleviate it with providing different data. So we push this issue to user side. Yeah, and yeah, so we're doing call with to the contract at the specified address. We sending some funds to it, and also we are specifying how much gas we want to allocate to that, and also we're providing the input data for the contract. And this data is actually just encoding the index of the action. So in our case, it's 0. So it corresponds to this variant. And this 4 bytes encodes basically a number by which we increment. Yeah. And let's execute this. Yeah, for now, it's the only way. But like we basically don't have EDSL right now, and it's the thing that is developing right now. Actually, yeah. So yeah, let's use this, and so this extrinsic is for calling this contract. Yeah, okay. Yep, so I think it is executed, and to verify that it's actually performing the task, let's just check the substrate storage for this corresponding storage key of that contract. And I have, because it's kind of hard to know which address is that, I have a special function that actually calculates this for me. And yeah, and let's take it and I believe it's already here, but let's, yeah. So, okay, here's the result, and it corresponds to 1, encoded in little endian format, and this is a specific thing for encoding the length of this data. So yeah, it basically worked. And then let's try to increment it once again by, I don't know. Okay, so. Damn it. Yeah. Wait a second. I don't understand that. So let me remove that and yep. Yeah, so this extrinsic is in memory pool, and let's wait until it actually, yep, it's mined, and then let's query the storage. And yeah, it looks like it's 8. Yeah, it seems it worked. Yeah.
Cool.
Yeah, sure.
The API which the contract has access to, like how it is set like. Obviously I cannot go and write files.
Yeah, it's a good question. Let me show you for now. So basically, it's more like Ethereum-like environment, and so for now we basically have bare minimum for writing contracts, and it's like get set storage, then call create, which basically is very similar to Ethereum ones, return, checking input size, and also like this. It also has a scratch buffer, and it's something that is not in Ethereum. So because of yeah, I didn't mention that storage in Substrate contracts have like arbitrary sized values. So you can put not only 32 bytes, but like arbitrary sized. And when you query it, you can basically return it in this user-specified area. Contract-specified area of memory. But then, it's like if the contract doesn't track the size of the of values that it actually puts in this in storage, then it could easily overwrite the memory of the contract, and this can be a bad thing. So because of this, we all arbitrary sized values are put into Scratch buffer, and then contract can actually query this buffer to actually load data from it. Yeah. So it depends actually. So you can't use anything that depends on files, threading, and things like that. But like everything that doesn't require like this operating system things like files and things like that, and can be compiled to WebAssembly, then you're probably fine. Yeah, so basically the system is very similar to Ethereum, and we basically have like gas metering very similar to Ethereum. Like every WASM instruction is metered, and every instruction in the block just metered. The prices of their prices are summed up and just deducted from some counter, and if it goes to the zero, then there's out of gas exception. Yeah.
So though we are planning on bringing in chromatic gas.
Yeah. Yeah. Yeah, and also the thing I wanted to mention that we about the API, that we're also thinking about giving the contract runtime a chance to call different modules outside of inside the runtime, so it can actually call. I don't know. Do you have an example?
Well, yeah. So there's governance modules, even the parachain module that would forward any potentially could have it open an entry point, a function call to forward messages into a parachain. So what you can imagine is a smart contract sitting on one parachain, sending out messages to a smart contract on another parachain, or sending messages into a governance system. So a smart contract chain like the Edgeware chain that was mentioned today could have smart contracts that manage people's voting preferences. That sort of thing. For the gas, it differs a little from Ethereum. One of the things that I wanted to bring into Ethereum, like when it was too late to bring it in, was this notion of chromatic gas, which is basically having 3 different kinds of gas. One of them for processing, one of them for memory usage, and one for storage. With the idea being that basically we can compute maximum gas per block in terms of resource usage for each of these 3, but it doesn't make sense that if someone gives up some processing power that they can instead bloat the chain by some storage, right? The two are not somehow mutually exclusive. So what we do is we actually have the resource usage independently for each 3, and then every contract gets, basically whenever you spend 1 gas on processing, you sort of get 1 gas on the other 2 for free, or vice versa. The gas sort of comes in white light, where you get all of the independent gases tied together, and then you can use them as you want, and what you don't use, either we haven't really decided, but it either gets sort of ignored or goes back into the pot, so that other things can, in principle, overspend. But what this does, it basically means you've got much better resource utilization, and you don't have the issue whereby you can bloat the chain by 3x what you should be able to just by using all of your gas to enter into storage and none of your gas on memory or processing, which is what the sort of scenario we're stuck with Ethereum.
Yeah. Yeah.
Oh, why not GPU as well? Well, maybe version 2. Yeah.
Would that gas system be encoded in one of these runtime modules?
Oh yeah, it would go into the contracts, right?
So yeah, this so for like the gas system is only a concern of contract module, and any other modules doesn't know about it at all.
So the specification of how the gas system works, would that be part of the contract module?
Yeah, I think so. Yeah. Somebody? Then.
Cool. So I'll mention one other thing, which is the account indexing, which is what we saw earlier.
Do you want to?
I can do it on yours, I think.
Okay.
I mean, I'll put up with Safari.
It's Safari, yeah.
But it's a nice little thing, so it's worth knowing it. Oh, can you? How do I get to Safari? Okay. So if you noticed before, while I was mucking around down here, can I make this bigger somehow?
You can do this little trick.
Just.
So there is, if you hold Control, you can scroll it like that.
Yeah, so if you notice up here, Alice has a, we've got two accounts here, Default and Alice. Default is this big long address, and Alice is this lovely little address, right? So this is these are both legit addresses, and if you in principle, if a substrate chain gets listed on an exchange, then in principle you can get one of these addresses. Right? This is just an address like in Bitcoin and Ethereum, right? But they both are. So Alice, this isn't some cunning name registry or something. This is an address. We understand? Yeah? We're good with this? Yeah. In principle, yeah. It will mean different things on different chains because it will reference a different account, just as the other one, the long one, would. So the long one is they're both base 58 representations. They've both got a checksum in them. They've both got a version byte in them. The difference is that the first one is a 32-byte public key from that represents a point on the ED25519 curve. So yeah, just the ED25519 public key. And the other one is an index, and that's why it can be so short. So every account if you use the SRML in Substrate, every account has an index associated with it. I should say every non-zero balance account, right? So every account that's active has an index associated with it. If an account doesn't have any balance, then it doesn't get one of these nice short IDs because there's no index associated. You can't enumerate every account. Then you may as well just use the 32-byte identifier. But if it's got something in it, then you can use this index instead to identify it. And we've got a mechanism whereby if it's within the first 200 or so, then you get to just use 1 byte, and if it's in the next 60-odd thousand, then you get to use the next byte, 2 bytes. And I think there's only like tens of thousands of active accounts of active accounts that have any real significant funds in on like Ethereum. So I suspect on Substrate chains we'll probably see most addresses to be fewer, basically be like 5 or 6 characters. it basically can look that up in its enumeration of all addresses. And as these things become free, so if an account goes to 0, Substrate's SRML balances module will automatically reclaim that address, right? So it basically deletes everything to do with it, and including this enumeration. And so if someone like has one of the earlier, I can imagine that there's going to be some like clamor to get the first 200 odd accounts that have, these four-letter addresses, because like there's only so many of them, and before long they'll go. But if someone like reduces their balance to 0 to the minimum, below the minimum allowed balance, there's this notion of an existential deposit, which is basically the minimum amount of balance you must have for your account not just to be deleted, bang, like that. Ethereum, Bitcoin don't really have this, which leads to an awful lot of dust accounts that have like an unspendably small amount of ether in it, so small that you can't actually send the transaction to spend the ether, but yet they're still recorded by the state, so they're still taking up a lot of space on disk. Exchanges are particularly bad for these things. They leave a bit of gas unspent, and that's just a tiny little bit of ether just clogging up the chain to the like 10,000 accounts a day sort of job.
That lead to something like please donate to that account and then no web page and another guy receives the donation. I can imagine that.
So this is why, in principle, yes. So if this account like reduces below the existential deposit and then someone else claims it, then that address won't last forever. So there's a couple of ways of dealing with that. The first is that address has in it a checksum, and that checksum refers to not that address itself, but to the account that address points to. So if they were to do it maliciously, it wouldn't happen accidentally. The checksum would look after that. If they were to do it maliciously, they'd have to mine an address that whose checksum was the same. And these accounts, these small ones, you can choose which address you want to use. You can choose which address format you want to use. And some of the address formats have like 8-byte checksums. So they'd have to mine an address that had like 8 whole byte, that shared an 8-byte hash, start of a hash with the address that's that's there. So I mean, I can see this not being so much of an issue. And to be honest, if you want an address that's like permanent, then sure, just use the big long one. Yeah. But if you want something that's like a payment address, or if you absolutely sure that you're never going to go below the minimum amount, then these small addresses should be fine, and they're a lot easier to remember. And the other, a notable other point is that if we delete accounts, and this came up in Ethereum, so Parity, we at Parity made a proposal, one of the EIPs, to sort of say, look, we should have dust collection. That was actually implemented on Kovan, right? We rolled it out to Kovan. And the issue, one of the issues is that it means that basically transactions can be replayed if you're not careful, because when you delete an address, you don't just delete the balance and reduce that to 0, but you also delete the nonce, which is counting how many transactions it's sent, which means the first transactions can now be replayed, or the very first transaction in particular can be replayed, and then the second, third, and fourth can, if that goes through successfully. And that's problematic, or it could be problematic, because if those transactions do something other than spending the balance, then you can actually put balance into the now 0 account, so it's now got cash to spend, and then replay those transactions to do this, to replay the side effects. This is why we brought in the transaction errors. So the idea is that when you construct a transaction, it's only valid for a particular period for the future. So you can make you can construct a transaction that's valid indefinitely. We allow for that. But if you do that, you've got to accept the fact that if someone else, if your account gets deleted, then the first transactions can be replayed.
So why would you allow for it if it has such a risk?
Primarily because there may be, well, firstly because we're generalists and we like to allow for as much as possible. And it's up to our users, who we believe are esteemed. We esteem them in terms of their intelligence, and we believe that they know what they're doing. I mean, everything goes wrong at some point. I don't believe in making tools. I don't believe in making kind of safety scissors for people. I think that at the level at least that we're at, we should be working with sharp knives.
But there should be a really good narrative for deal with risks.
For sure. But I would put this on the user level. So I think this is, if you read some of the other chains, they issue kind of not warnings, but directives to their middleware and user level, like UI engineers. Say, look, this, you can cut yourself. The chain doesn't protect users from doing this stupid thing. So it's up to you to protect them by putting in these warnings, and we will do the same. So, for example, if your wallet knows you've issued transactions or doesn't know that you haven't issued era-limited transactions, and sees that a transaction you're about to issue would remove your account, would delete it, would take it below the minimum amount, then it would basically bring up this big it would either not let you do it, or it would bring up a big warning saying, "Are you sure you know what you're doing?"
But this is a role for the middleware to signal that.
Sure. Yeah. So if we don't want to hamstring people that are developing on the platform, we want to inform them, and we want to inform them when they should hamstring the people who are using what they're developing, or at least give them information to make sure that they don't shoot themselves in the foot.
To implement checksums in the addresses and that's also.
Yeah, it's true. I mean, there's maybe a trade-off to be made here. Checksums seem a perfectly reasonable thing. I mean, most address formats have checksums in. The original Ethereum didn't, and that was a really big pain. So that was just lesson learnt. In this case, I don't think there has been a lesson yet to be learnt, and I think it's such a really easy thing to protect against. Like, either wallets shouldn't let you construct transactions without errors. That should be a niche thing that you have to build your own applications to do. I mean, there can be. I can imagine applications where errors don't fit. For example, suppose you've got something like a plasma kind of chain, or a state channel, and you need this transaction to potentially last indefinitely, because that's the only guarantee that the other side has, that you won't just pull out after the era has ended. Yeah, it's like there's no other way of doing it, and there you just have to ensure that for your specific niche use case, there is no way of reducing that balance below the existential deposit. But in most use cases, user-level tools can make sure that you don't shoot yourself in the foot. Yeah.
How does your nice transaction look like when you have these variables? Do you use padding or?
Say again?
So when you serialize the transaction as a row,
Oh, when you serialize the transaction.
do you need to use padding, or how does it work with this indexing?
Hold on. So when you serialize a transaction.
You need to put like addresses, right? In the row.
I see what you mean. Yes, can we carry? Yes, the answer is yes. We can carry our concise address format into transactions as well. So normally we would have to put a 32-byte identifier for each address for the sender and the receiver. Irritatingly, so one of the things that if you read about ED25519, they'll be like, oh yeah, it's really good. It's got like compact signatures. Its signatures are smaller. They're only 64 bytes instead of 65. What they don't tell you is that unlike ECDSA, you do need to put the sender address in there. So yes, you might shave a byte off in terms of the signature, but you have to add an extra 32 bytes on because you have to tell it who the sender is. I mean, Bitcoin provides both, but whatever. That was just a questionable decision. Ethereum doesn't. We don't bother encoding the sender in the transaction because we derive it directly from the signature. You can't do that with EDDSA. With ED25519. So Actually, signatures are 96 bytes.
kind of wondering if you have a kind of collision between the big address and the small one when you put all the padding.
We have a binary format, so we don't have padding. We have a binary format that basically uses 33 bytes to encode one of the 32-byte addresses and uses 1 byte to encode the small ones and so forth. And you can determine what it is from the first few bits. Yeah. So if you use these small addresses, you shave off like 60 bytes, potentially a couple more from the transactions. And that's a pretty decent saving. It basically cuts transactions by 2/5 of the size.
Can you maybe talk a little bit about the using Substrate as a relay chain? Like in your presentation, you had one slide about that.
As the relay chain.
Yeah, maybe some challenges.
Yeah, I mean, so the Substrate comes from the relay chain. So when we started coding Polkadot, well, when we started coding Substrate, what has become Substrate, that was just called Polkadot. And although even before we started, I had in my mind it was going to turn into Substrate, I didn't really mention that to the other devs. So they were a little surprised when I started renaming stuff. But yeah, it's the biggest challenge is kind of the thing that I mentioned. It's getting that level of generalism while still making things be easy to while still making it easy to write the things that you want to be able to write. So that's what, you know, any design of language or API comes down to this, getting this trade-off right. And it ultimately comes down to expressivity. So expressivity of a language in a domain is really just how well you can make it easy to do the things that you want to do and make it possible to do everything. Yeah, and bringing those two closer together is what we call expressivity, or what we call a good language or a good domain language. And you know, Substrate has a similar challenge. Getting it general is not so easy. It's something that I, you know, kind of wanted to do even since CPP Ethereum, but not having had all of the experience, it wasn't so easy to do at the early days. But it gets a bit easier with having coded a couple more. Say again? Is data deleted when it's deleted? Okay, so what was the question again? Okay, so specifically with smart contracts or with runtime modules and the Substrate in general?
I don't recall, is the state separate from Substrate storage?
Not really, but smart contracts kind of do their own thing to some degree. But okay, I'll talk about Substrate in general because that's what I can answer. Yes. It, I see. I know what you mean now. I know what you mean. Yes, no. Contracts work differently. No. Okay, so we have archive mode that keeps everything around forever. It doesn't run in archive mode by default. It runs in a standard pruning mode by default, which basically clips any state from blocks that are old enough, like after 100 or 200 or so. If what you're talking about is like in Ethereum, when a contract deletes something, if that contract, if that call into that contract turns out to be exceptional and everything gets rolled back, then that delete doesn't happen. In Substrate, in the basic runtime module, in the basic sort of core, we don't do rollbacks, right? So as soon as something gets written into storage or deleted from storage, it's actually deleted. And unless the entire block gets rolled back because it panics, then it's done. That thing's deleted, and there's no way you don't have checkpointing in there. If you want checkpointing, which you may well want, it goes into the as a runtime module library, and the contract runtime module library that does smart contracts actually implements checkpointing. So it implements something that is basically a minimal form of Ethereum, but that has most of the stuff of the Ethereum environment. And the only difference is that it doesn't run in EVM, it runs in WebAssembly. Because WebAssembly is kind of cool and sexy and fashionable and hipster. Mm.
Maybe you can explain what is done today, or what's the plan on doing in terms of quality regarding the runtime, and what is possible when things go south.
Yeah, I mean, to some degree, runtime upgrades and these sort of out-of-band state changes are specifically what we do, how we manage what happens when things go south in other ways. So ultimately, there's the same safeguard, if you want to call it that any other chain would have that doesn't have a governance system, which is it can always be hard forked, even if the governance system of Polkadot, Substrate, whatever goes Ori. I sort of take a two-prong approach and say, well, on the one hand, we want to be reasonably conservative and try to get solid reviews of our proposed governance mechanism, and or use governance mechanisms that already exist in real life and that we have some idea will probably work okay. With the other prong being try it out as much as possible on testnets that actually have value before we put it onto a network that has lots of value potentially. And this is where the Edgeware project could be very helpful, and potentially others like it, to really provide a network where no one's losing anything if there's no cost to it going down or being problematic or having to suffer a reversion, but there is real value at stake because it's got tokens that are worth something. And that I think is a really nice middle ground to sort of go and try a bunch of stuff that we think probably works okay, but we can't be sure, to really try, empirical testing, try it in real life. In much the same way that when the psychologists want to run a new experiment, they get a bit of money and they sort of say, look, if you do this right, you get 50 quid and this is the instructions, off you go. Kind of the same thing. And we did something similar with the Olympic testnet back in POC 9, POC 10 days with Ethereum to try and get people to kick the tires of what would become the main net before we released. I think Olympic was not a failure, but I don't think it was a great success. Not that many people took part in it, and it didn't uncover one or two of the bugs that came up, which we would have otherwise hoped. And I think a testnet that has real value, maybe less value than it would otherwise have, but still real value, is probably a much more market-oriented and therefore probably more successful way of trying to incentivize people to break it or otherwise test it.
Talking about testing, testing in Ethereum is not very great in terms of how all the clients kind of coordinate.
Mm-hmm.
How, not in Substrate, but in Polkadot will that be different in terms of everyone being
Yeah. So I mean, you know, Ethereum had the consensus test. It had a decent fuzz testing. Although I will note that when we implemented Parity, we found 2 points where the consensus test didn't cover, and we had to add new consensus tests. It's a hard thing to do. With Substrate, we kind of work around it a little bit by saying there's a single WASM reference on chain, so it's basically like a machine executable reference spec. I think it's questionable whether that's such a great thing. I mean, the Bitcoin guys love that idea because it's like they've got their reference implementation, Bitcoin Core. I kind of like the yellow paper for not being machine executable, but yeah, I mean, in Polkadot and Substrate's case, it was largely forced upon us anyway. In principle, there could be multiple implementations of the same runtime. Like, that's something that I explicitly provide for in the versioning. I'm not sure if it will happen. The foundation, the Web3 Foundation, is looking to find teams that, yeah, cool.
That's why I asked.
Okay, yeah. So I mean, I'd like to see it happen. But as for whether we could really come up with better consensus tests than what we have for Ethereum, I'm not sure. It's a really tough thing to do without literally paying someone to painstakingly go through the specification, every single conditional, write a test for, and I mean, this gets exponentially complex as the different modules, I mean, you're looking at kind of 2 to the number of conditions, potential number of tests that would have to cover everything. It's crazy. So I would probably just go for taking out a month's rental of a supercomputer and running a huge amount of fuzz tests. I think that with a well-designed fuzzer, that should probably provide as much protection as you would otherwise get.
Is there such a thing as a gas price, or how to estimate the transaction cost of those? Or is there any mechanism to prevent free transactions?
In Polkadot, so there is a mechanism to prevent fee transactions. Basically, transactions under the Substrate model, which Polkadot adheres to, transactions must, under the Substrate, the SRML model, which Polkadot adheres to, I should say, transactions must pay for their space on the chain. So there's a fixed fee for a transaction, and there's always, I mean, you can set it to 0 if you want, but in principle, there's a fixed fee that a chain can leverage. And this is something that can be changed and upgraded and all the rest of it. It's just a parameter. And there's also a per byte fee that's charged per byte of the transaction as it's encoded on the chain. So that's non-negligible. That's non-negotiable. They have to be paid. Beyond that, there isn't. If you want to charge additional fees for what the transaction's doing, then that's up to the chain and the runtime modules and the sort of the code that you're writing yourself. You can charge for what you want. Polkadot will probably have some fees associated with the creation of balances, with the creation of accounts. So the balances module has a fee schedule that you can again customize. If you, depending on how much you want to charge for the sorts of things of creating new accounts, reaping old accounts, transferring balances. There's a bunch of things that you can customize. What else? Other modules. I think most modules actually don't specify much of a fee schedule. Because most of the modules, the governance modules do have a fairly complex system of deposits. That's mainly to address sort of a game theoretic concern of a potential quadratic attacks, quadratic cost attacks, where certain algorithms are order n squared to run or order mn to run, and you have to make sure that m and n can't both get too big. It's okay if one of them gets kind of big, but you need to make sure that they can't both get too big, otherwise you end up sort of going off into the distance in terms of the cost. And that's managed through, as I say, a set of deposits and basically incrementally increasing the cost of one or the other, depending on how big the other one is. I think that's probably about it. I'm not so worried about literally charging every single clock of processing like gas would do. Partly because a lot of operations are order one, or they have like a reasonable maximum that is not, they don't really go proportional. The user can't force, or the transactor can't force anything over a particular maximum, and that maximum is relatively insignificant. And I would look upon it more or less as the Bitcoin chain does, where it's fine basically to just charge for space on the chain for the size of the transaction and not think too much about the processing costs, because they will be dwarfed by the storage costs. Obviously in smart contract land it's much more important to charge for everything, because users can potentially write infinite loops and all the rest of it. So the contracts module does indeed make sure that there's a proper costing mechanism for that.
So one of the things that caught me off guard at first is that these fees are not going to the validator or the miner, but are being burned.
Yeah.
So why was that chosen?
It's not a final design decision, to be honest. But part of the reason is that it makes a lot of sense when block production is on a individual basis, like miners. So miners are competing with each other to produce these blocks. It's not really the case in the consensus mechanisms or block production mechanisms that I see Substrate working under. In Substrate's case, it's really more of a sort of collective thing, and it doesn't really make sense to reward one over another. And partly it's, I guess, can I remember the other reason? I think there was, so in some sense when you burn fees, it's a little like paying all of the other participants. I guess, yeah, okay, so the reason that miners collected fees in Ethereum was because that's what they did in Bitcoin, and the reason that miners collected fees in Bitcoin was because eventually the block reward was going to go down to 0, and that would be the only thing that incentivized miners to do anything. That's not the case in Polkadot. In Polkadot, the validators are incentivized like permanently through the reward system. That basically means no dilution will happen. Their sort of percent, or their ratio of their stake compared to everyone else will remain the same. They're sort of dilution protected, and everyone who's not part of the validation nomination sort of system would get diluted. And because that's in place, it doesn't make so much sense to then reward them extra for the transaction fees. That said, it's not a final decision, as I said, and I'm like, it's something to talk about over the next few months and see if there's a compelling reason.
You're not like creating an incentive. Could that lead to censoring some addresses, or
Yeah, I mean potentially. I'm not sure we really see that in real life. There's plenty of instances where Ethereum transactions go through for 0 gas price. Censorship, can always happen. But, it's just if you're going out of your way to censor some transactions, there's a cost associated with that selection mechanism, and that cost may be insignificant. I mean, that cost may be the price you're willing to pay. May be substantially greater than the cost of not collecting a couple of microcents of fees. So.
I imagine, for example, exchanges or things like that, like players that they can have an interest of delaying like other exchanges transactions.
for sure. But if they do, then adding a small transaction fee isn't really going to make much difference, unless you know the transactions that they're dealing with are a micro transactions, in which case.
Does it also kind of play into like the idea of staking in that there's more randomness involved and not kind of a win to like a race to win that block and get those fees associated with that block?
Yeah, I mean, that's it. So staking is more of a sort of collective pursuit rather than something cutthroat. Yeah, I got a feeling there was another reason, but I can't remember what it was now. But as I say, it's not something that I'm happy for this to be a continuing conversation, and you know, if it turns out that it does make sense for the block producer to take these fees, then fair enough. At this point, it's just the simplest code. Like it's one line of code for you. I don't have to. Basically, suppose you have 20% of the chain that is 20% of the total capital contained on the chain, total tokens that is part of the staking system, and the market effects are such that 5% of that 20%, so a quarter of that 20%, or 5% of the total, are being replicated for their rewards. So I mean, this is a hefty reward, right? 25%, but whatever. Then, in order to prevent the rich get richer situation of the chain, where validators just everyone gets diluted, and all of that dilution is favoring the validators. Their percentage of the total stake just keeps going up and up and up and up until eventually their total of the amount of the chain approaches like 100%. To avoid that situation, we place a well, if we say it was 20 to 80, then we place an according amount, so 4x in our 20 to 80 ratio of the amount of that reward goes into a pot, right? So so we've got 20%. A quarter of that gets paid to the validators. So we're going to mint 25% of the chain's tokens again. Yeah. So we're going to dilute by 25%. We take a fifth of that 25% and give it to the miners, so validators, whatever. So that's that a fifth of 25 is 5, so that's their 5%. Yep. And with the other 20%, which basically is a fifth of 80, sorry, a quarter of 80, 4/5 of the 25, that gets placed into a sort of community DAO for the chain. Not too dissimilar from, you know, the thing on Dash or even like the DAO, although less buggy, hopefully. And that will be used. There's already a Treasury module in here. It's very simple, but there's a Treasury module that lets you sort of put forward ways of spending, and they can be voted on. And then the idea is to basically allow additional modules to spend money from this pot, and they can be sort of integrated through chain upgrades. It can also be a lottery. It can also be a reward for people that accounts that are willing to bet on the price going up if you've got an Oracle feed of the price. So if you're willing to bet that the price goes up and the price does indeed go up after a period of time, then you can get paid from this pot, and if it goes down, then your money gets put into the pot. So there's all sorts of interesting. Don't think about that too hard. There's all sorts of interesting. Oh yeah, you can like what I showed you. Like the thing is, what I was trying to think of a toy runtime module that would extol like that I could code live, you know, that wasn't so big that I couldn't code live, but also that sort of got across a degree of sort of generality that this provides. And unfortunately, everything that you can code live pretty much will look like a smart contract, because smart contracts are just tiny little bits of code that you add to blockchains. But what I did with the extra module, although it looked a bit like a smart contract, it worked very differently, right? This was a deployment of code that would be run natively and that would sit, in principle, in the same place as the smart contract, bit of the Ethereum state transition function, or the EVM, or whatever else. You wouldn't think about coding, you wouldn't even consider coding an EVM interpreter as a smart contract. That would just be zany, right? That would just be crazy. It would run so slow and it'd be really horrible. But you could do that in one of these modules because it operates at like a 10x lower level. So you get that 10x in performance and in... Well, it uses that. It uses a Substrate runtime module for its parachains management.
Is there staking and delegation in the proof of stake system? Like, for example, can you delegate your stake to a validation?
Yeah. I don't call it delegation because that's kind of got a loaded meaning now that EOS uses it. In particular, when you delegate a stake, you don't get punished if the party that you delegate to misbehaves. And that's hugely problematic in terms of getting incentive correctness. So we call it nominating. And the critical, as I say, the critical difference is that when you nominate a validator with your stake, you lose your stake if they misbehave. I mean, they lose theirs first, but if they don't have enough to pay for the misbehavior, then you lose yours.
And is there bonding?
Yeah. Yeah, so you, this is to get around the nothing at stake issue, long-range attack. Yeah. So, yeah, it's bonded. The moment the assumption is it'll be about 3 months bonding period, but it will be at least as big as the expected period between releases of the binary of any software that sort of interprets this chain. So
when it comes to syncing a brand new node, then that needs some kind of a secure source. So maybe is it planned that you do something like checkpointing on proof of work chain, like for example on the Ethereum mainnet?
no, the assumption is that the most recent checkpoint will go into the software itself, and the bonding period is sufficiently large that, and the software will be released sufficiently frequently that the most recent software release will be holding currently bonded validators to account. Okay. Say again? You can if you put it in yourself. I use fixed point for anything that needs points. So. One more. If you remove floating point, then it's deterministic. Cool. Okay. I call an end to this. Do you want to do it? Do you want to do the end?